And here we go. Okay, so we are very, very happy and lucky to have today with us François-Xavier Briol, or just FX. And thanks for joining us. FX is going to, so FX, first of all, is a lecturer at the Department of Statistical Science at UCL, London, and also a group leader at the Alan Turing Institute. And yeah, he's coming today to talk about robust inference, and we are all very much looking forward to your talk. Thanks, FX.
Thanks, Rizzi. Thanks for the invite. So as you said, I'm going to talk about robust inference for most of the talk. I think my talk is a little bit long, so I'll do only like part of it, but I'll leave some little tasters of the other sessions as well. I thought before it starts, I would talk a little bit about the Alan Turing Institute. So last week I was actually in Helsinki to meet with a few people, including Luigi and Otto and a few others. And one of the reasons for that is because there's a partnership between the Turing Institute and FCAI. And one of the things that we're trying to do is trying to figure out what are the kind of existing connections between the two institutes, and also trying to see what we can do to kind of improve and strengthen these connections. So I've got only one slide on this. I won't bore people for too long with non-technical things, and after that I'll jump to the technical stuff. But I thought, just since I have all of you here, I'll just do one slide on this. So the Turing Institute is the National Institute for Data Science and AI in the UK. It's quite a big institute in terms of number of people and universities attached. So there's 13 universities across the UK that all have Turing fellows, i.e. kind of professors that are affiliated with the institutes in one way or another. It's mostly structured through a bunch of different programs. So I'm part of this data-centric engineering program. And the point there is to develop statistical and machine learning tools for solving big engineering problems. But as you can see here on my side, there's quite a few different ones. I didn't write them, all of them. I mostly wrote down the ones that are more likely to be of interest to the people on this call. And all of these programs have kind of directions of research, and some have group leaders like the DC, which I'm in. Others are structured slightly differently, but they're all trying to kind of tackle certain goals in these different areas. So as I said, there's been some sort of agreement signed between FCAI and the Turing, and that was a few years ago. And at the moment, Arthur Clammy and I are running some sort of small survey. A few of you have actually emailed from this call already, but it should have been sent around. And so basically, we're just trying to get an idea of what is already happening between the two institutes and what we can do to make it kind of make these opportunities kind of strengthen them, let's say. So I've put our email addresses down, but probably the easiest thing is to actually just have a look at your emails, and you've probably received something about the survey. If you haven't, you can also email me and I can forward the survey to you. Okay, so that's the only non-technical bit of my talk. I guess for the rest of the talk, what I'll do is talk about a line of research that I've been working on for about, I'd say, 3 or 4 years now, which is about designing inference methods that are in some way robust to model misspecification. And most of the line of research there has been for so-called intractable likelihood models. And I'll explain what each of these terms mean as we go along. But basically, intractable likelihood models are models that are, let's say, so big that you can't write down all of the things that you would need to do standard inference. And so you have to kind of circumvent this issue by working with slightly different things. And I'm sure many of you know about some of the things that I'll talk about. But here we go. So I thought I'd mention briefly some of my collaborators on this. Probably the main one to mention is Ayush, who's actually one of the FCAI postdocs. So some of you probably know him. Okay. And I should say, maybe an advertisement for the Turing is most of this work actually comes from, being at the Turing and meeting with people there and all this. So if you do want to meet with some of these great people, you should come and visit us. Okay, now I'll stop my advertising. Okay, so the sort of problems that I'm going to be interested in for this talk is mostly parameter estimation. So I've got this slide here just to set up notation, but I'm sure all of you know the basic setting for parameter estimation. So I'm going to have some data, these xi's, and they're going to be RID random variables coming from some distribution Q. And I'm going to observe the xi's, but I don't know what Q is. And so I'm also going to have a parametric model, which is just a family of probability distributions indexed by this parameter theta. And my goal is going to be recover the parameter theta such that p theta star, so the theta star being the one I've recovered, is equal to Q, i.e. I'm trying to recover what distribution generated the data from said data. And that's kind of the standard parameter estimation task. So it's mostly here to set up notation. So xi is the data, q is the true data generating process, and p theta for any theta is my parametric family. And here, this condition will be possible, of course, if the model is well specified, but will be relaxed later in the talk. Okay, so earlier I said that one of the challenges with intractable likelihood models is that you cannot actually do standard inference. And what I mean by that is, well, if I don't have a likelihood, I can't do simple things like maximum likelihood estimation, because here the likelihood term in red is going to be unknown, and so I can't actually maximize this quantity. Similarly, in Bayesian inference, I normally start with a prior and update that prior with a likelihood. Of course, if I don't have access to a likelihood, then I'm slightly in trouble. And overall, there can be lots of different reasons not to have access to a likelihood. So it could be that your model is too complicated to actually be able to write it down. Or it can be that the model, well, evaluating it would actually be way too computationally expensive. And so it doesn't really matter which case, but essentially in this talk, I'm going to assume you can't evaluate this likelihood term. And this likelihood term is simply going to be the density of p theta here. Okay. Right. So I thought I'd give a couple of examples of models where this happens. So this is a kind of AI seminar series, so I have to have my machine learning application. And I'm sure many of you have heard of things like deep generative models, VAEs, energy-based models. All of these models, usually you don't have access to a likelihood, or at least it's not so easy to kind of work with it. But most of the work that I've been doing has been more in the physical sciences, and well, just in the sciences generally. But one of the line of works that I've worked on is with Ayush, who's the person that's at FCAI, which is on intractable models that show up in fields like engineering, in this case, telecommunication engineering. So here, the sort of problems that you're interested in is you have two antennas, a transmitter here and a receiver here. And your model might represent some sort of physical process of when messages are transmitted from the transmitter to the receiver. And the more and more details you add in your physical model, the more complicated the model becomes, and the more challenging actually writing down this likelihood becomes. And in some cases, it becomes completely impossible. I'll skip this one because I won't have time to do it. So so if you don't have a likelihood, or you can't evaluate pointwise the likelihood, you have to find other things that you can do to actually deal with these sorts of problems. And usually, even though you don't know the likelihood, you might know something slightly different, or you need to use some other piece of information to kind of solve this parameter estimation task. So one setting which is quite common is when you have normalized likelihoods. And by that, I mean that your likelihood, which is intractable, can actually be written as something which is possible to evaluate, this p tilde, divided by some constant that is unknown. And so p is unknown because of c theta, but you can still evaluate p tilde. Now, in those settings, the main challenge is that usually this constant depends on theta. And so if you're doing maximum likelihood, say, you can't just maximize the top bit because c theta also has a big impact. And similarly for Bayesian inference, the theta bit is important. And so this is one kind of line of work that has been followed by quite a few different researchers. So in the Bayesian setting, it's usually called doubly intractable models because this is unnormalized and also the posterior is unnormalized. In more kind of frequentist approaches, there's this score-based ideas, so where you work with the score function instead of this, and I'll kind of go back to that later. And that's closely related to this score matching idea, which also relates to FCHI. And okay, so that's one way in which your model could be intractable, but still have information that can be used. Another type of model that or setting that you could be in is when you know absolutely nothing about the likelihood, but you can easily simulate from your model. So by that I mean, if I fix the parameter value theta, I can get IID samples from p theta without too much trouble, let's say. But I don't know anything about the likelihood. So all I can do is simulate for new parameter values of my model. And again, this is something where, okay, I don't have the likelihood, but I still know something about my model, i.e. how to simulate, and I can use that to do parameter estimation. So again, there's been quite a few different approaches that use this. Just to name a few, there's the method of simulated moment, synthetic likelihoods, ABC, etc., etc., etc. Okay. So what I've done so far is kind of talked about this problem of intractable likelihoods, then given two examples of ways in which a likelihood can be intractable, but where we still know something or perhaps enough about the model to actually do inference. Now, one claim that I'm going to make is that very often in those kind of big intractable likelihood models, your model will actually tend to be misspecified. So what do I mean by that? Well, what I mean is that a lot of these models, for example, in the sciences, will be basically scientists and engineers trying to make their best, to do their best at kind of representing some sort of real world process. And so they're going to add more and more details in their mathematical models. But very often, they're just still a very rough summary of reality. And what that means is that maybe there's not a single theta star such that p theta star equals q. I.e., it could be that your model, there's none of the elements of that parametric family actually correspond to the true data generating process. And in those cases, I would say, well, it's usually said that the model is misspecified. And it's important to understand what are the impacts of this misspecification when you try to do parameter estimation, and whether we can do anything to kind of prevent this issue. So just to give you a really trivial example of this is obviously not an intractable model, but it's just to give you an idea of what I mean. So imagine I have a normal model, so with unknown mean. And let's say that my data was actually generated with a normal with mean 1, or at least 90% of the data was generated from that normal. And 10% of the data was generated, well, is actually fixed at some point y. And y is going to take slightly different values. So if I do standard Bayesian inference, or something similar, what I'll end up with is a posterior which looks like these curves, depending on where y is. So if y is very far away, let's say at 20, you can see that my posterior is shifted really far away from what we would hope to recover, which is this actual mean, which generated most of the data, which is 1. In fact, in this case, it's not even anywhere near 20, and so it's really recovering complete garbage. And that's potentially problematic, because here what you can see is that the posterior is also quite confident about this value. And this is purely due to the fact that the model is misspecified, so your kind of uncertainty is meaningless. Now, in this talk, what I'll do is talk about how you can work around this and develop methods which account for misspecification, or at least allow you to kind of mitigate some of the effects of it, and get you posteriors that look a little bit more like this, where if you have a little bit of perturbation, let's say, as if here, where you only have 10% of the data that's kind of corrupted, you can still recover sensible values around 1, which is what you would hope for a method which is robust to, at least in this case, some sort of outlier misspecification. Okay. So the kind of roadmap for this talk is going to be developing methods for intractable likelihood models that are fairly easy to implement and robust to mild model misspecification. Here, I insist on mild because obviously if, all of your data is garbage, then you can obviously not recover anything. And there's obviously going to be a sweet spot in the middle where you'll still be able to recover something. So here, what I mean by mild is your model can't be too different from the true data generating process. Okay. And let me just check time. Okay. So most of the rest of the talk is going to be based on some notion of distance between probability distributions. And I'll explain how you can use these distances to create parameter estimation tools. So here, throughout the rest of the talk, I'm going to have some abstract distance d, and all I'm going to require from it is that it's always greater or equal to 0, and 0 if and only if the two inputs are the same. And the choices of distances that I'll cover are so-called kernel-based notions of distance, and I'll explain what that means in a second. But for those of you that know a little bit about kernel methods, obviously the choice of kernel will be crucial, and most of the talk will be about how you can choose the kernel in a sensible way to get all of these benefits here at the top. Okay. So in this talk, I'm not going to be very, let's say, fixed on one inference approach. So I know some people really care about Bayesian statistics, others really care about frequentist statistics. I'm going to do hopefully quite a lot of it in one talk. And I'm going to show you how you can use, just from a notion of distance, can get all sorts of different schemes that fall in each of these categories. So just to start with, I'm going to have Qn, which is going to be an empirical measure, which essentially represents my data. So this is just some notation for me to be able to kind of input it into this distance. But Qn is just my true data. So one way in which I can estimate parameters, if I have a distance, is looking at the distance between my data and any element of my parametric family, and then say, okay, I want to recover the true data generating process. So I'm going to find a model that's as close as possible to my data, and that should be a good enough guess. So here, I'm just finding the value of theta, so the parameter value, such that my model is as close as possible to my data. And something like this would be called minimum distance estimation. So that's one way. If I want to be a bit more Bayesian, there's this method called ABC that I've already mentioned, which is specifically for intractable likelihood models of the kind of generative sense. And so here, roughly speaking, the procedure is you sample some values from your prior, and then from that parameter value, you're going to generate from the model, and then you're going to compare kind of simulated data to your true data and decide if they're closer or not. So here again, you need some sort of notion of distance, perhaps between data sets in this case. There's also this whole line of work on so-called generalized Bayesian inference. And here, so you get posteriors of this form, and they look very similar to kind of your standard posteriors. So you start with a prior, but then the update is not based on the likelihood, but on some other notion of loss, which can be taken to be a distance between the model and the data. And actually, this plot that I showed you a few slides ago about these posteriors, which are still very focused on this parameter value 1, so the slightly more robust posteriors were all obtained with something of this form. And I'll talk about that in a few slides. And finally, there's a few other ways of doing kind of Bayesian inference with distances. One of them is this non-parametric learning framework, where maybe I'll just leave it at you kind of generate some sort of generalized posterior by solving a lot of minimum distance estimation minimum distance estimators. Okay, so I've said a whole lot of different things, but hopefully, as you can tell, all of these different methods, these different ways of learning from data, are all based on the distance. And so, of course, crucially, what will happen is that whatever distance you choose to input into each of these frameworks will have a huge impact on whether this is actually a good framework or not. So what I need to do now is tell you a little bit about these distances. Okay. Now, in terms of distances, you could obviously take whatever you want, whatever your favorite distance on distributions is. But the main challenge with most distances is that it's really hard to actually evaluate these distances in practice in the case of these intractable likelihood models. So just to start maybe from a very general class of distances, these so-called integral probability metrics, these are distances that compare distributions by when you integrate functions, how different these integrals are. So if I want to compare P and Q, I'm going to integrate some function f against P, the same function f against Q. If they're different, then I know that P and Q are going to be different. If they're the same, at least for that one function, then there is some evidence that the two, that P and Q are the same, but maybe one function is not enough. So you kind of do this over a whole class of functions. And there's lots of distances that you're probably familiar with that fall into this class, where you just slightly change this class of function h here. So the Wasserstein distance, the total variation distance, the Dudley metric, they're all examples of these integral probability metrics. And as I mentioned, the main challenge usually is that you can't actually calculate distances. So here, I'm just going to explain it for this class of distances, but it's true for many distances that people kind of use in probability and in statistics. So here there are two challenges. There's this supremum, which you might not be able to compute, and also these two integrals, which you might not be able to compute. So actually evaluating this distance is very hard. Out of the examples that I've given, one exception is this Wasserstein distance, where this becomes an optimal transport problem, and for which lots of computational tools have been developed. One other possible choice for this function class h here is to take a kernel-based function class. And that's what I'm going to be doing in this talk. So in this talk, I'll be taking my function class to be a unit ball of RKHS functions. So these are kind of special kinds of functions which can be written, the way you should think of them is as some sort of sum of evaluations of a special function called the kernel. And one example of kernel is this Gaussian kernel here. So this is just to give you an intuition of the sort of functions that we're talking about. So you can think of, I'm kind of taking this supremum over weighted sum of these Gaussian-like term. Okay, now if I do that, the very nice thing is that I can actually get rid of this supremum here in closed form just due to the property of this class of functions. So essentially what I've done is I've been a little bit clever thinking about my function class such that I remove some of the intractabilities. And so if I choose this class of function, I'm going to end up with an expression for this integral probability metric, which is of this form. Well, this is the squared version of it. And this is called the maximum mean discrepancy in this literature. And I didn't invent this. This has been around in machine learning for a very long time. And it started with some of the work on kind of hypothesis testing from Arthur Gretton and co, also at UCL. In fact, this sort of quantity has been around for much, much longer, more in the applied mathematics literature. But I'll leave that on the side. Okay. Now, with this sort of distance, what I could do here is, if I had samples from P and Q, all of these integrals could be changed into sums, and I could then have something which is easy to estimate as well. So one thing I can do, if I have samples, is to do something like a U statistic approximation, something like that. Now, this sort of distance is really perfect for something like generative models, because in generative models, I would have Qn being my data, so that's fine. It's already an empirical measure. And I could just sample from my model to then estimate DMMD or DMMD squared between my model and my true data. So this sort of quantity can be plugged in directly into all of the various inference framework that I talked about earlier, distance estimation, ABC, et cetera, and can be used directly to tackle generative models. So due to kind of time constraints, I won't go too much into details on this one, but there's another line of work that I've been working on, which is more about what you can do in this unnormalized likelihood case. And here again, the idea is very similar. You essentially take some sort of class of functions, which is rich in some sense, but also leads to a distance which is computationally convenient. So I'll put it there. This is called the Kernel-Stein discrepancy. It looks very ugly because I haven't had time to go through it. But the key components is that it only requires access to what's called a score function. So the gradient of the log density and nothing else. And it can again be evaluated from samples. If Q contains samples, then you can evaluate this in closed form. And this distance is going to be perfect for these so-called normalized models. But again, I won't talk about that later. It was just to kind of give you the idea of where I was going with this unnormalized models. Okay. So now what I've done, so I started to talk by saying we have some challenges with intractable likelihood models. One of the main problems there is that we have this issue of robustness that we want to kind of input into our inference frameworks. So if the model is misspecified, we want to be able to do something about it. And I've explained how you can kind of derive parameter estimation methods from kernel-based distances. And so now, basically, the rest of the talk is just thinking about kind of having fun with all of these different combinations of kind of inference framework and distance. So there's quite a lot of papers on this, where you can study exactly what happens in terms of all of these parameter estimation frameworks, both in terms of robustness, but also kind of ease of implementation and maybe efficiency, and all of these questions that come up once you have a method to do kind of statistics. Okay. So in practice, all of the methods that I talked about will be able to, in some way, trade off various things. So one of these might be kind of sample complexity, or at least, let's say, ease of implementation of the method. It could also be statistical efficiency, so how fast do I recover the true parameter from data? And also this idea of robustness. And the way you trade off these three different things will usually be based on this kernel. So the kernel is basically the central quantity. I've only given you one example so far, but obviously I'll talk about this a little bit more. That will allow you to kind of decide where on the spectrum of sample complexity, statistical efficiency, and robustness you want to be. So, for example, in kind of classical statistics, it's really well known that you can't necessarily have both statistical efficiency and robustness. So if you want to learn very fast from data, if your model is misspecified, you're going to usually learn very fast the wrong solution. And so usually there's already a trade-off here, but there's also going to be a trade-off about with how easy these methods are to implement. And I think the answer to what's the optimal choice of kernel is still very much unclear, but at least we have some ideas to answer the question of how should you pick this kernel depending on what your preference is out of these three kind of things. Okay, so one first consideration is this idea of sample complexity. So for both of the MMD and the KSD, so the two kernel-based distances that I talked about, you can get results which say with high probability, the true distance that I care about will be approximated by a sample-based version of it at a rate which is square root of n. Okay, so that's already something that's very nice. It's also something that's quite rare for other distances. So for example, if you take this Wasserstein distance that I mentioned earlier, this would be something like n to the minus 1 over d, where d is dimension of the space. So that would be a lot slower. So here, the kind of sample complexity is already very favorable. But there is this constant here at the top, ck, which depends on the choice of kernel. And usually that will have some impact. So whatever choice of kernel you choose will really impact this sort of constant that you get here. So already you can see the kernel has some impact in terms of how easy it is to do statistics or machine learning, or at least let's say parameter estimation in this case, because for all of these methods to work well, I need, well, basically this quantity to go to this quantity fast in n, and this is, well, highly dependent on k. Similarly, kind of how nice the map between the distance between p theta and q in terms of the parameter is really depends on k. And so again, if you choose k in slightly bad ways, it'll make kind of either doing optimization or running MCMC really hard for the sorts of methods that I talked about, because the map is very, basically not very nice. Okay. Another kind of desirable thing for a method is to be, let's say, efficient. So if I think about specifically the minimum distance estimation framework, but really this is the same, well, similar results can hold for all of the other methods. You essentially want your true parameter to, sorry, your estimator to converge to a true parameter as fast as possible. So you want to learn from data very fast. And usually in this minimum distance estimation framework, what you can do is write this as a central limit theorem. So you say, my estimator approaches the truth at a rate which is square root of n. And so here the kind of variance of this Gaussian tells you how spread out your estimator is. And so here again, this highly depends on k. And you can derive the exact expressions for this or for this. We've done this in the papers. And you can see that there's a really big impact of the choice of k. And also it's not super easy from seeing the expressions to kind of determine how k impacts all of these, but it definitely impacts it quite severely. Okay. And finally, if I think about robustness, so usually robustness is very often in the sense of this kind of perturbed model where you have kind of a true model plus some perturbation. Here I've put some outlier. It could be any sort of other distribution that's put in here. Again, you can show that using kind of classical tools from robust statistics, that the estimators that I talked about before all are so-called robust. And usually robust, there's not just a single definition of robust, but there's a whole load of different definitions of robust that depend on what you perturb with and what you assume this perturbation looks like. So this would be kind of outlier perturbations, but so it would fall in this bias robust definition, but there's quite a few different other definitions that fall into this category. And again, myself and a few others have kind of showed that both of these distances can lead to quite strong robustness to misspecification. And again, the choice of kernel really impacts how robust you are. So let me just take one example to just go back to what I was to what I started with. So if I take one of these KSD distances, I do a generalized Bayes procedure. So this is exactly the example from earlier. This is if I use standard Bayesian inference. This was my new method, so with this KSD distance. And as you can see, I'm again getting posteriors, which are a lot more concentrated around 1, which is the true parameter value. And this version is if I choose a KSD distance with a kernel, which is specifically designed for robustness. And again, here from the theory we derived in these papers, you can very easily find what these choices of kernels should be, or at least you can find sufficient conditions that the kernel needs to satisfy in order to ensure you have this, this robustness. Okay, so I think I have 8 minutes and I should leave some time for questions. So what I was going to do next is show you some kind of applications of this, but perhaps that's, let's say, slightly less the interesting bit of the talk. So I'll just highlight briefly the kind of sort of results that we get. So there's 2 applications, one which is the one with Ayush. So maybe I'll focus on this one. So again, here we have these generative models of how signals are transmitted. We did a lot of work and basically we get some very nice results. Here the models are very clearly misspecified, but you still are able to kind of recover a reasonable parameter value for each of these models. The other one that I wanted to show you was a big graphical model of kind of protein signals. And again, here we're able to show kind of strong robustness by choosing carefully the choice of kernel. So I'll leave it at that, just so I have time for questions. But in general, these kernel-based methods are really great, mostly because they allow you to trade off these 3 different things that I talked about. So robustness, efficiency, and ease of implementation. Another nice thing that they have, which I didn't get to talk about because I had to skip, is that kernels can be defined on all sorts of complex data spaces. So for example, if your data is a time series, like in the application of Ayush, you can design a specific kernel to kind of tackle these problems. And that makes all these methods really powerful because they can very easily be adapted to new kind of challenges. So if you have data on time series, maybe on manifolds, all sorts of weird data spaces. But of course, there's this kind of double-edged sword in the sense that they're really great because you can trade off all these things, but then also you have to be able to pick the right kernel. And this is not something that's easy. But I think a lot of the theory that we've developed in these papers that I mentioned along the way really allow you to narrow down reasonable choices of kernels that can be used depending on what you prefer, whether you prefer misspecification, robustness, or say efficiency, etc. So I'll leave it at that so that hopefully we still have 5 minutes for questions. Yeah, that's it.
All right, thanks. Fantastic. Yes. Yeah, I think I definitely have some questions, but let's see if anybody from the public has other questions before. Otherwise, well, people maybe are thinking about it. So, okay, yeah, Sami, I was expecting a question there.
IFX, really
Hi.
nice talk. So it was great to have the tutorial. It was easy to follow at all steps, and still you were able to say something modern as well. So is it? I began thinking we could maybe continue on this on another time. When we were discussing with you, we were discussing on how to formulate the robustness and maybe one thing that wasn't in classical statistics, or at least I'm not aware of, is what has now what many of the deep learning approaches seem to be implicitly doing is to essentially model all the possible kind of alternative generators that may come and disturb your signal, which goes maybe one step beyond what you would have as having a perturbation, but which is maybe spot noise or something, which of course only makes sense if you have more samples. But now, if you do have more samples, but your kind of real signal, you only have as much as earlier, but now you have more samples that are then corrupted. So is there? Do you think some of that could be formulated in ways that you are working on, or in some other ways? I'm not following all of the deep learning literature, obviously, so maybe somebody is doing exactly this already.
So me neither. So my answer is going to be quite limited on that. So there are. So I think if I understood well what you're saying, okay, you can estimate a parameter from data, but then suddenly you get more data, and you want to be able to be robust to that. No, maybe I didn't.
Okay, so yeah, sorry, that was unclearly explained. So I'm assuming that there are alternative generators, so that come and corrupt your data, kind of, for instance, additive generators that are structured, so you can't make simplifying assumptions, but you do have, they reoccur in many of the samples. So in principle, you could estimate them. And if you have estimated them from the other samples, then you would be able to discount them from your signal in those samples where your signal is present.
Okay, I see. Yeah, so I think a lot of I think it's in some way complementary what's done in this literature versus what you're talking about, because I think in this literature, of kind of robust statistics, the kind of more classical tools that we actually use in this work, what you're kind of assuming is that there is a perturbation, but obviously you don't know it, and you want to be robust to certain perturbations. Now, of course, if you can just estimate what the perturbation is, then you can try to include that in your model. And I guess it sounds a bit like these deep learning techniques that you're talking about, try to do that in some way. So here, I think what these approaches try to do is they try to say, okay, well, we won't ever be able to model every single type of perturbation. And maybe now you can with deep learning, I don't know. But anyway, at the time when these tools were developed, that was the idea. And so you want to be able to kind of say, well, okay, even if I can't estimate the perturbation, I can at least try to make sure that my methods won't be kind of completely destroyed by having one of these perturbations. And I guess it's in some ways slightly simpler of a thing to do, because you're not trying to estimate something, you're just trying to not be impacted by something. And it seems a bit, at least intuitively, slightly easier to do from a practical viewpoint. But could it be included? So I guess, I guess we could try to learn something like a good sort of perturbation model to be robust to, or something like that. Maybe that's a way to go a little bit in between the two.
Right. Yeah, I'm just have a hunch that the trade-offs that must be made there, in contrast to having completely non-informative models for the noise, there may be something interesting there. At least the deep learning can do something. I mean, the question could now be that what happens if you go to lower sample sizes than what deep learning currently is considering? That there might be some interesting trade-offs. But yeah, sorry, I'm eating up too much time. Thanks for the great talk.
No worries. Well, one more thing that I would say is that I guess all this notion of robustness becomes less and less relevant in cases where your model is extremely flexible. Because if your model can model anything, then you're never really misspecified, right? Because there's always going to be a parameter value which recovers the true data generating process, or at least something close enough. And so in some ways, these robustness questions are more interesting, I think, in models which are not overly parameterized like this deep learning methods. Mostly there because you can just make your neural nets more and more complicated, and then eventually you can recover anything, if that makes sense. So I don't, there's probably some interesting questions there.
Yeah, thanks. Yeah, actually, the question I wanted to ask is very similar to what Sami asked, which is, I mean, here you're presenting robust inference. Let's say, so should we make robust inference or should we build more robust models? And because and for example, in the example that you built, so if you have a finite set of potential perturbations you're thinking about potential, so I mean, I could build in that finite set into my model, but I understand that, of course, it's a slightly different approach, and what you were presenting, of course, it's a framework. It is some, so I understand some of the advantages, but it's from a say first principles point of view. So what was the right thing? Because
so I guess if you think about some of the applications, for example, maybe Ayush is here and he can say something more sensible than me on this. But if you think about these models here, essentially there's people that spend entire PhDs, etc., developing more and more complex models. And here they put a lot of work into kind of representing all of the physics. So of course you can say, well, you could create a model which has more and more details and so won't be misspecified. But in some way, in a lot of science, you're not quite yet at the point where you have the perfect model, right? Otherwise, essentially the field is completed and you don't have much more work to do there. So here the sort of tools are much more about kind of acknowledging the fact that we don't always know everything, or at least are able to represent everything in our models. And we still want to have some sort of reasonable kind of parameter estimation tools.
Yeah.
And
sorry, so I think that second can tell us a second, because say, no, I understand perfectly that, but what I mean is, you can have a Gaussian noise model, you could have, a student T model, right? And one is more robust than the other. It's not necessarily representing the ground truth. It's not the student is closer to truth, it's just it's more robust to outliers.
Sure.
So that's kind of the direction I'm saying. We could build more robust models, more robust, noise models, etc. And the question is, so why should we do that, or when should that, or when should we do it? Robust inference. So tweaking the inference or tweaking the model, and tweaking the model. I haven't done that work on tweaking the inference yet. I find it very interesting, but I also say it looks like to me that we are kind of modifying something. Let's say in some ways that I don't know exactly how to do it. For example, how to calibrate when you start tweaking the inference, and you have the problem calibration of the thing. Which by the way turns out also in deep learning, Bayesian deep learning has the problem of calibrating inference. Even if they try to do proper Bayesian inference, then you still have problem calibration. So there are all these issues that I'm not sure I personally say how to handle. So what's your view on that?
So I guess my view on kind of tweaking the model versus tweaking the inference methods. I guess let me think. So if you go for like a so-called robust model, you do have the issue that if your model is not misspecified, then you don't recover the true parameter because there is no true parameter. So with these methods, you can be in a setting where if there is robust misspecification, then you control for it. But if there's not, you still recover the right parameter because you're using the right model that you actually believe in. So I think in some ways, I'm quite happy with people to use both, and I'm sure there's advantages for both. So I don't have a very strong view on that. Yeah, I'm sure both would be helpful. I guess it's more like, I'm sure in those kind of applications, people have spent so long developing their model. If you start telling them that they have to modify their model into something that maybe they don't believe in, they might not be very happy. I don't know. Again, Ayush might be able to comment on this specific application. But I don't have a very strong view on it. And I guess, yeah. So there was also a question on Bayesian deep learning and kind of calibration there. So I have quite maybe negative view of Bayesian deep learning, mostly in the sense that I think a lot of the time, the kind of priors that you see there are a bit nonsensical in the sense that, no one actually believes in the priors that you get. And so, in many ways, kind of the sort of posterior uncertainty that you get there is difficult to kind of really believe in, I guess. And so in there, I would guess that there's less of an issue of misspecification because of the, what I talked about earlier. If you have a really highly over-parameterized model, you're less impacted by misspecification. But I think there, the problem is more about, how do you do proper prior selection in some sort of sensible way such that the uncertainty at the end is somewhat sensible. And to me, it seems like there's a lot of kind of attempt at this, but I don't think it's anywhere near solved, right?
It's very much an open question. There are also actually even recent debates about whether it's the prior. I mean, some people say yes, some people say there is something more. It's been a lot going on.
Yeah.
Okay, but sorry, yeah, we can go very short. So I think we can declare, yes, it's officially ended. Thanks again, FX, for all the